Now, in general, our solution to the equation we started with, f net equals negative kx, comes out with the x of t function a sine of omega t plus b cosine of omega t, where omega equals the square root of k over m, which I've written again down here as something very, very important. We'll talk more about that. Now, by simple high school level trigonometry, we can, had to pause, there was a bright streak across the top here. I had to do something about that. Okay, again, our general solution, a sine of omega t plus b cosine of omega t, can be put into the form c cosine of omega t plus theta naught, where c and theta naught depend on the relative, depend on the values of a and b. And this is, again, a basic high school level trigonometry operation. Not that I think it necessarily gets done in most high school trigonometry classes, but that's the level at which it is. So you should understand how to combine these to get this, and if you don't, you should brush up on your trigonometry. Okay, so this is equal to this for the appropriate theta naught and also c, so I better write that in there. Now, I want to know what the reference circle picture would be for x of t equals c times the cosine of omega t plus theta naught. In other words, for this version of this function. Remember that we showed that this function had its specific reference circle picture, and we referred to the reference circle picture for this function, but how do they combine to give us one of these? And once they do, how do we model it? Okay, so what we do is we draw a circle, and that's a really poor circle, but okay. The circle has radius c centered at the origin, and we have a point moving around the reference circle, so we have our r of t vector following that point around the reference circle with at angular velocity omega. We also call that angular frequency. Then we have the angle theta naught. When t equals 0, we have c times the cosine of theta naught. So that if we were to project this point on the reference circle up here, we would have the t equals 0 position on the x-axis, and that would be the t equals 0 position of our oscillator that's going to oscillate back and forth. Omega t is, well, angular velocity times the clock time. If we started here at t equals 0, well, then wherever we started at t equals 0, omega t is how far we've gone since that point. So we have omega t here, and that's where we are. Okay, theta naught plus omega t. Now we'll say that this angle here brings us to a point that's coterminal with theta naught plus omega t. And I should expand that statement just a little bit. Let me do that. Okay, this little note just says this angle here with the positive x-axis brings us coterminal with theta naught plus omega t. So I say coterminal with theta naught plus omega t because theta naught might actually be an angle such that we make more than one revolution around before we come to this position. And omega t might be big enough that instead of just going from here to here, we go around once and end up here. We go around twice and end up here. We go around any number of times and end up here. Then we're coterminal with the angle that I've represented here. So, with that little caveat, and hopefully you understand circular trigonometry well enough to understand what I just said, with that caveat, this is our r of t vector, corresponding to c cosine of omega t plus theta naught. Circle of radius c cosine of omega t plus theta naught is just going to be our projection of this r of t vector onto the x-axis. So here's our angle that's coterminal with theta naught plus omega t. Cosine of that angle is what we're going to use to project this point down to here. So now this point is c cosine of omega t plus theta naught. Now we have a model that has a starting point down here. As t starts to increase, omega t starts to increase, bringing us progressively around to here. As that occurs, the projection of this point will move out to here, and then we'll move back to here. So that between here and here, our projection has our projection is the position of the oscillator on the x-axis. We'll have gone from here out to here and back to here. C cosine of omega t plus theta naught is a model of that motion, a model of what we call simple harmonic motion, starting at this point, moving out to here, back to here, and so forth, with angular frequency omega. Recall or note that C cosine of omega t plus theta naught is our solution of x double prime equals negative k over x for omega equals square root of k over m. Okay, so omega is the square root of k over m from this equation. This is our solution, and this is our general solution. Theta naught could be anything, so we can match this solution up with any initial position on the reference circle in order to match our motion up on the x-axis with the projection of the reference circle motion starting at that position. Important to understand that omega equals square root of k over m comes from this equation, and to understand how it comes from this equation. Also, what omega means. Omega is simply the velocity, angular velocity of our r of t vector around the reference circle, or if you want to call it the angular velocity of the point around the reference circle, that would also be valid. C and theta naught are our two expected integration constants. So in solving this equation, we get two constants. We first got this solution, but now we converted it to this form, and again we still have two constants that are determined by the constants that we have for the original equation. This gives us an extremely powerful picture of simple harmonic motion.